So now problem set for chapter 13. So start off with calculating mass percent. What's the mass percent of solution that has 27.5 grams of ethanol and 175 grams of, or 175 milliliters of water? I even said grams because it's 1 gram per milliliter. So I see that 175 milliliters I just converted to grams all the way. But if it's a different liquid without a specific gravity of 1 or density of 1, then you'd have to do that calculation separately. So we'll go ahead and convert the water to mass. And so mass percent is mass of whatever over the total mass times 100%. So for the ethanol is the solute. So 27.5 grams of the solute. And the solute, again, is the thing that's the less. And the solvent is whatever is the most. The solute is what's dissolved, and solvent is what is dissolving. So looking at this, we get 13.6%. And then with the 2 sig figs there. So hopefully that makes sense. So let's do another one. A soft drink contains 11.5% sucrose by mass. What volume of a soft drink in milliliters contains 85.2 grams of sucrose? The density of the solution is 1.04 grams per milliliter. This is going to be scary because 85 grams of sugar is a lot of sugar. So how are we going to do this? Well, we need the mass of sucrose, which is given, and then from that, with the density, we get the mass of solution, and then convert over to the volume of the solution. So already given is a mass percent, and then the density of the solution's given. And so if you see here, using the mass percent, then as we're going to divide by the percent here, and it's if you see the units there, how it all works out. So just using the 11.5%, so 100 gram solution, 11.5 grams of sucrose. So starting out with 85.2 grams of sucrose, we have to divide by the mass percent to get the units to work out. You can see specifically to cancel out the grams of sucrose. And sucrose is the C12H22O11. And then to get to volume, divide by the density again to get the units right. And then if we get 712 milliliters of solution, so that's still quite a bit of soda, but 85 grams for that. I mean, that's about two sizable, medium-sized cups of soda. So it's a crazy amount of sugar. Ew. So does this kind of make sense? And I think it does make sense. I mean, and especially you can see how sweet the sugar is with that. So let's look at molarity. A molarity is moles per liter. So you see this is the most common concentration that chemists use. Mass percent is used, or volume percent is used quite a bit in like colloquial things. So for instance, vinegar is typically 5% by mass of acetic acid. And alcoholic beverages, the proof, it's actually twice the volume percent for alcoholic beverages. So if 40 proof whiskey is, well, it is usually 80 proof. 80 proof whiskey is 40 parts alcohol by volume to 100 parts of total solution. So, but in chemistry, we typically use molarity. So you're going to be doing lots of molarity calculations if you study chemistry more. So what's the molarity of a solution? That you have 15.5 grams of sodium chloride in 1.5 liters of solution. So it's moles per liter. So first, you got to convert the mass of sodium chloride to moles of sodium chloride, and then the moles per liter. And the total solution is 1.5 liters. So we get 0.177 molar. So the capital M is molar, and that's moles per liter is the units on that. So let's use the molarity in some calculations. So how many liters of 0.114 molar sodium hydroxide contains 1.24 moles of sodium hydroxide? So we're going to have to use the units on this. And the idea is that we got to start with the amount, and then we're going to go to the liters, and we're given the concentration. So start off with the amount that we need is 1.24 moles of sodium hydroxide. Divide by the concentration, moles per liter, and we're got 10.9 liters of solution. So you can see, again, dimensional analysis, when you look at this, you want to make sure the units cancel when you get the unit that you want at the end. So does it make sense? Yeah, I think this does make sense. It's reasonable, especially with so I mean, looking at this, that doing they call it back of an envelope calculation, you can say like the 1.24 moles, you can say about 1 mole, and then the 0.114, it's about 0.1. So you think you need about 10 moles in that. So to me, looking at this, I'd expect an answer around 10. So this does make sense. So let's look at the ions. The same thing previously, but we're just adding the other step that we look at the total number of ions. So get the molar concentration of sodium ion and phosphate anion in a 1.5 molar solution of sodium phosphate. Looking at this, so find the molarity of each. But if you look at sodium phosphate, there's 3 sodium ions to every phosphate ion. So there's a 1-to-1 molar ratio between sodium phosphate and phosphate, and there's a 1-to-3 for sodium phosphate to sodium. And sometimes it's even referred to as TSP. So like you can go to hardware stores and buy TSP, and that's trisodium phosphate. I'm using the proper term. Proper term is sodium phosphate. So that's just me being the professor snob. But the colloquial term for this is TSP, trisodium phosphate, or even just TSP. So with that, sodium is 3 times, so 4.5, and the molarity of the phosphate is 1-to-1, 1.5. So with that. And let's look at this solution dilution thing, and I use this all the time. With this is a very it's easy when you're to do dilution calculations using these equations. So what volume should you dilute a 0.1 liters of a 15 molar sodium hydroxide solution to obtain a 1 molar sodium hydroxide solution? And we in the back in the lab, we call these a stock solution. So we prepare stock solutions, and then we dilute them to the concentrations we need. So use the formula M1V1 equals M2V2. So use that and solve for the second volume. So solving for the second volume, one equation, one unknown, put in the terms, and you get 1.5 liters. So which means you put the 15 molar solution into a 1.5 liter volumetric flask, or if you don't have that, then you put it in a liter, or if you have 3.5 liters, and then you fill it up to the line, and you put it either, if you have a 1.5 liter volumetric flask and you leave that one, or if you have 3.5s, if you don't want to do the dishes, kind of thing, you can just fill up one, then you put it into a bigger beaker, and then fill it up twice. So the only thing is that when each time you do that, though, you add a little bit more error when you're doing this. But of course, that's a practice in the lab. This is more the theoretical stuff. But let's move on and talk about stoichiometry. So now including these mole calculations in stoichiometry. So consider this precipitation reaction. 2 potassium iodides plus lead nitrate makes lead iodide, lead 2 iodide, and 2 potassium nitrates. So how much 0.115 molar potassium iodide solution in liters will completely precipitate the lead 2 ion in 0.104 liters of 0.225 molar lead nitrate solution? So my training right away as I look at this, I'm like, okay, moles to moles. So I'm like, okay, how many moles of lead do we have? And now we need twice as many moles of potassium iodide to do that. So of course you can do this, you can look at it that way, just do a straight mole calculation, or you can also do go through the steps of the dimensional analysis. So you don't always have to use dimensional analysis, although it is very convenient. But let's go ahead and use dimensional analysis. So start with, like I said, think moles. We got to get to the moles of lead. How do we get the moles of lead? We take the volume of the solution, then divide by the concentration of the moles of lead. Then we convert to moles of potassium iodide, and then by the concentration we can get the volume of solution. So and the molarity, with the molarity of this, you need twice as many amounts of potassium iodide. So and this is from the balance equation. This is the middle step of the dimensional analysis. So again, start with the volume of the solution. times the concentration, moles per liter. I know I said divide, it's multiply. You got to get then the moles of lead. Now we convert from moles potassium iodide to moles of lead, and then now we divide by the concentration to get the volume. So 0.407 liters of potassium iodide. And this is something that you would need, like, so if you're trying to get rid of anything so you don't put lead ions in the environment. Of course, this is a small scale thing. I mean, if you're talking about 100 milliliter, 104 milliliters or something, I mean, this is nice for the chem lab, but I mean, if you're like we're dealing with industrial processes, you may be dealing with hundreds of tons of stuff. So just keep that in mind if you go on to apply this to a real world application. Does this make sense? Yeah, because if you look at the concentrations, the concentration of the potassium iodide is a half of that of the lead, and you also have the 2-to-1. So you'd expect to have kind of 4 times as much of the potassium iodide as you would the lead. So I think this makes sense. So it makes sense about 4 times. That does fit within the kind of, am I doing it right? And does this make sense? And that's kind of what you can do when you're thinking about it. Does it make sense? So we're going to go from molarity to molality. And molality is something you use in freezing point depression and boiling point evolution, increase in boiling point. So elevation, that's the word I'm looking for, boiling point elevation. So let's calculate this out. So 17.2 grams of ethylene glycol dissolved in a half a kilogram of water. What's the molality? So the molality is moles per kilogram. So first thing to do is convert mass of ethylene glycol to moles. So we have moles of ethylene glycol and divide by the kilograms of solvent, and then from this we get 0.554 molal, little m. So capital M is molarity, and little m is molality. So be careful with this because little m can also mean milli. So you have to look at the context of this. So little m by itself is molal, and little m with like a little m and then a capital L, that's milliliters or 1,000th of a liter. So keep that in mind. I mean, why would we not make this more confusing for you guys, right? So the milli 1,000th, it has to be attached to something else. So keep that in mind. So we're using freezing point depression. So new solution, 1.7 molal ethylene glycol solution. What's the freezing point? So the freezing point depression is going to be the molality times the Kf, and that depends on each individual liquid. And for water, it's actually pretty low for water. There's bigger ones for especially organic carbon-containing molecules. But 1.7 molal times 1.86 degrees Celsius per molal, and we get 3.2 degrees Celsius. And now this is like this next step is usually where students mess up. Don't forget to subtract the freezing point depression from the original freezing point. And for water, it's at 0 degrees, so it makes it easier. So don't forget to do that. And so subtract it, and then the freezing point is negative 3.2 degrees Celsius. So keep that in mind. Don't forget to subtract at the end. You've done all the hard stuff. Don't mess up on the easy part. So don't make that mistake at the end. Don't forget to subtract the freezing point depression. Now moving on, we have boiling point elevation. So same solution, 1.7 molal, and get the new boiling point. And so same procedure, except you have to use the KB instead of the KF, and we get 0.87, and then we have 100.87 degrees Celsius is the new boiling point of this solution. So notice something though, it was -3 for the freezing point, and not even 101 for the boiling point. So you can see that for water, at least, the freezing point is usually more pronounced when you have this, and it kind of expands the liquid phase of the water or whatever liquid you're dealing with. And we are at the end. Thank you for listening.